Moving from data science to observability, let's welcome Roman Grytskiv, senior developer at Booking.com. Booking.com arguably runs the biggest graphite metric system setup in the world, writing about 50 million data points per second via relays and store about 500 million metrics in total. Roman will share how they solve the problem of putting down tens of millions of metric data points per second, cover the design, resiliency achievement, and high loads on hundreds of boxes managed with Nanotube, their high-performance metrics router. Thank you for joining us, Roman. We are live.
Thank you. So as already announced, I'm Roman Grytskiv. I work here at Booking.com, and this presentation will be about the Nanotube. Nanotube is our innovation and our new development as a router for metrics. So I will start with just giving a very brief overview of observability at Booking.com. There are very many parts, and this overview is just in the context of Graphite. Graphite is the main metric storage and also serving system that we use. And just going step by step. So the whole life cycle of observability and of metric storage in particular starts from input. We have multiple input sources. The data comes from bare metal boxes. We also have an event system that is quite large that also sends metrics. Also, there is Kubernetes. And as a one small particular case, you also can send metrics via distributed load balancers too. And as already said, we get around 50 million data points per second. This all is stored in Graphite. This is what we will be discussing in this presentation. This is the main focus of the talk. And we store around 500 million metrics there. After metrics are stored, same Graphite also takes care to move them to the presentation layer, which is on the right. And we have various components there as well. We mainly use Grafana to render the metrics. We also have an HTTP API in Graphite that is later used by various alerting systems that read from Graphite. Also, there is alerting in Grafana itself, of course, as well. So basically, this presentation will be about solving the problem of scale and solving the problem of storing high numbers of metrics and also getting in high numbers of metrics. And we will focus on Graphite. And I will go into detail just right now. So here is the basic life cycle of the metric. And here presented the components and their roles in a more abstract way. So we are talking about Graphite here. So customer submits metrics. Our main way of submission was still is, but not that much. It's through a sidecar on a box, and the box runs the submission router. The submission router then routes this to the main router. That one routes it to the store, and store saves the metric. I will go briefly through the roles that these two first components play. So the submission router does like first level of control over what metrics can go in, which cannot. So this is the first level of observability and filtering other things that relate to control too. It also does the load balancer functionality when it sends metrics to main router, plus the resiliency as well. because as I will show in the following slides, how you send to the main router can contribute to resilience. And then the main router does the duplication of the data and the sharding, which of course contribute to resiliency too, because that's the basic things. Our stores don't handle the duplication and sharding by themselves. And so these things are handled by the main routers. This makes main routers quite important and also a little bit more involved. The store itself handles, of course, the storage, and also it does the aggregation. We don't do aggregation along the way when metrics go to the store. Then we go to the reading part. So here is a basic data reader. It does a raw data retrieval from the store, and it does the deduplication because we store several copies, and also does the healing of the metrics if at some copies some data is missing. From there, we go to the main front end that has some higher level functionality like query parsing, does the mathematics, image generation. It serves the HTTP API that goes to the customer, and it also goes to Grafana. And to be more specific, so here are more specific components that we used before. This is our old setup. So as a submission router, we use SURelay, the same SURelay we used for the main router. The SURelay was started at Booking, but it's not Booking owned at the moment. And the SURelay is where the most innovation will happen. Actually, the replacement of it is where most innovation will happen. So these things will change. The storage that we use is GoCarbon. It's not Booking owned, but we have nice collaboration. The links to the GitHub repositories are just on the slide if you're interested. Then the first level of data reader is called Zipper, and the second level, the high level, is called Carbon API. They are in the same one repository called Carbon API. They're both Booking owned, and they are both written in Go. And so we had a number of problems with the right part, the routing part, which is the SURelay highlighted in red. I will go through these problems a little bit later in the presentation. And so the change that we did, and new thing that we developed, is we replaced those things with Nanotube. So Nanotube is a new product that does routing of the incoming metrics. And here already you can see some changes. So in terms of what it gets in addition to what SURelay supported, it also supports OpenTelemetry gRPC protocol. And it also can run a daemon set on Kubernetes. So the SURelay could not run there. It only could run on some particular box, mostly as a sidecar. And further, I'll go into a little bit more detail about how this part works, the writes, the top half. So we can have a look at the writes in a little bit more detail. These are the same components as on the previous slide, just a little bit zoomed in. So the metrics come in to a submission nanotube that can be running on a box, or it can be running on Kubernetes as well. We support a couple of protocols. We support the line protocol, and now we also support OpenTelemetry gRPC protocol. The line protocol, how it looks like, is very, very simple. It's three values separated, two parts separated by a space. So it's path of the metric, the value of the metric, and the timestamp. It is a little bit limiting when working with it. And that's one of the reasons why we support OpenTelemetry now as well. Another thing why it's so nice that we support OpenTelemetry is because we now can do the hybrid setups and do the migration. So this is what comes in. And then the submission nanotube sends the metrics to the main nanotube setup, the main set of routers. And what it does the load balancing with health check. We do the load balancing ourselves. We don't rely on any distributed load balancers. And the reason for that is we want to be very stable and solid when it comes to outages. So we try to rely on as little systems as possible. Then the main router, the nanotube, does the roles of sharding. So it does consistent hashing and also does the role of replication. Here, the circles are storages. Each circle is the sharding circle. We send usually 3 replicas of each matrix. This what guarantees resiliency when the storages fail, of course. So here is the slide that shows the whole thing in full detail. On this slide, different colors are different data centers, or DCs here, or availability zones. You can call them that as well. Sub-NT is the submission router, submission nanotube, NT is the nanotube. In the center are the storages. Then FE are the front-end reading parts. LB is the load balancer, C is the clients. And just going through one sample write and sample read, I can illustrate how this whole thing works. This is all in the context of the previous slides as well. This is just a more detailed picture. So if you follow the red arrows, this is the route of the writes. When we get new data points, they come to the submission nanotube first. Then we do a load balancing to the nanotube, the main router. This load balancing sends 1 copy and has failover, health checks, things like this, what all the load balancing should have. Then the main router sends 3 copies, as described on previous slide as well, to the storages. The storages that we save to are highlighted in bold. So we do the duplication. So from now on, we store the data. And now we can follow the route, how the reads happen, how the data is actually retrieved. So we can start from the top right and follow the green arrows. So for the client sends a request, the request goes through a load balancer. We usually just have a simple round robin across all data centers. We get the request on the front end. Then the front end does a broadcast to the storages. And in the simplest case, this broadcast just goes to all the storages there are. But we are trying to be smart, and we have algorithms that try to figure out where the metrics are more likely to be present. So we send the request to the storages that are likely to have the metric. Then we get them and we serve them back to the customer. That's how we work. A couple of things to highlight here are, as you can see, the submission nanotubes only talk to nanotubes in the same DC. This is to withstand network cuts that are cross DC. This is for the reason of resiliency. Even if a data center was completely cut off from the other ones, we will still be working perfectly fine within this data center. Also, you could think about the nanotube circles here as not separate nanotubes, but clusters. This is what we run. We run nanotubes that are grouped in clusters. And the reason for that is to have isolation and to have different routing depending on the source. And that will be important later, because this is one of the things that we would want to improve in the future, and we will be working on. So, sorry. So moving on. So the question is, why Nanotube? Why we build it? What are the reasons for that? So the reasons is we are trying to resolve problems of scale. So as already mentioned, we have a very high number of metrics coming in and also stored. So a lot of the problems we are resolving, they stem from that. So, and the first things are resilience and stability. So one of the problems that we had with C-relay that we are trying to resolve is to have independent targets. The target is where the router sends the metrics, and the problem could be that when one target fails, the others should not be affected, but in the old setup, we had other targets affected when a single target would fail. So that would present a significant problem, because when the targets are correlated, then the replicas are not really replicas anymore, and we can have the loss of data. Another thing about resilience is that we need to be stable under high load. And the C-relay could not be stable under our load in the newer version. So it would work fine on low loads, and that would actually be completely okay for most people's setups. But with our numbers, it has proven to be unstable. We have tried multiple times to run it, the newer versions, but they would just be unstable in the end. So the stability and the resilience. Then the features, we would like to have Kubernetes support, of course. So we do a major migration to Kubernetes in Booking at the moment. And we also would like to have OpenTelemetry support to make it possible to have hybrid setups to enable people having migrations to OpenTelemetry. Another problem we are solving is observability. So the Nanotube has much more metrics, and also the metrics are in Prometheus as compared to the C-relay that we used before. The metrics there were sent downstream with all the other metrics. That meant if something went wrong, the visibility would disappear. You wouldn't know what is happening at all. Then the maintainability. We applied simpler design. We have good test coverage. We have a separate full test suite for Nanotube that does full end-to-end tests. We also have parsable config, and it's in Go. It's just easier to maintain. Then the performance. It's better, especially when the configurations are complex. The performance is significantly better. And I'll expand on this a little bit later. The ownership, it's easier for us to make changes, fix bugs, features, and the simplicity. I will expand on that later a little bit as well. The simplicity is very important in our case. It contributes to performance, contributes to resiliency. So going into detail on the whys, first is the performance. So this is the CPU load during move from C-relay to Nanotube during the migration. This is what happened when we replaced the old router with the new one. This is the load on the machines and the production cluster of routers. So the CPU load were down 3 times. So the performance is way better with Nanotube. The use of the memory also went down like 5 times, from 5% on the machines. And as the result of that, because the performance is better on our clusters and our scale, we were able to immediately release around 100 relay boxes because they were not necessary. This capacity was not necessary anymore. So just directly save money. we can sustain around 400,000 records in and 1.2 million out on a single box of Nanotube without production config. Well, you could ask, like, what is a production config and what is general compute in this case? Well, we have fairly fat servers and our production config is quite complex. For a more typical, simpler configs, we can sustain much higher loads for a single Nanotube. And then the question is why? Why performance is so much better than I think that's written in C, which is lower level language, also was optimized. And the reasons are because it's simpler and design is simpler, and it was from the ground up designed with concurrency in mind. And this also allowed to have better performance. I'll go on those things following slides. So the simplicity. So here, just to illustrate how much simpler the Nanotube is we can compare the C-relay config. This is the old config that's on the left with Nanotube config that's on the right. You can immediately see the difference just visually, but to going into detail, the C-relay had its own format of the config, and it was DSL. It had a full language to define configs, and the language had branching. You could even have loops, and this data structure, this config had to be parsed into an abstract data structure, and for each record, you had to execute that. So of course, this is computationally very heavy. And the configuration was imperative, so the execution went from top to bottom. This increased the complexity quite a bit, so it's much easier to make mistakes. It also had various bonus things like custom validation and things like that. And here on the bottom, you can see the illustration, what I mentioned before, that we had the statistics and the metrics that were sent downstream. And that would interfere with the visibility in when it came to when something goes wrong, when it came to outages. And on the right is a Nanotube config. So it's in TOML, so it's default language is by default supported in many places, much easier to work with, and it is declarative. So this is the biggest upside. Basically, what you can see here is all there is. It's the full definition, almost, not the full, but 95% of the definition of what is used in Nanotube. So it's extremely simple. Basically, there are definition of clusters and the definition of rules, how you route to clusters based on the prefixes and regex matching. That's all. And the question could be, is this sufficient? So in our experience, this is sufficient in almost all cases. Just as a full disclosure, that we actually support some of the imperative expressions for backwards compatibility that we use during migration, but we are looking to get rid of them and have things purely declarative. But in general, our config is declarative. This makes it much simpler to work with. And this also allows for fixed data structure and fixed way of processing things, since it's extremely predictable. There is only a couple of ways things can go and be routed. So we can avoid the abstract data structures that have to be evaluated every time. We also can do a lot more optimization. So this is the main reason why we have better performance, even though we have a higher level programming language. It's also much easier to maintain and work with as well. Then comes to design. So design is another reason why we get better resiliency, better performance, and it works better on scale. So I'll just go through the components of Nanotube bit by bit. So you get the connections that are going in here. And we have a listener that listens to the connections, accepts them. Then through these connections, we get the data points, and they go to the main queue. And then they are picked out of the queue by multiple routers that run concurrently. And these routers route them to appropriate clusters, and the clusters consist of hosts. Each host has its own queue and its own sender. Sender is the part that actually connects to remote host, or we could call target, and sends the data there. And now let's go through why this is beneficial. So we have a main queue. This gives the resiliency to load, because when we have spikes of load, we will get data accumulated in the main queue first and then released to the routers, so the data will not be lost. And even if the data is lost because of overload, it usually is lost in small batches. It's not, it creates a lot of small holes, and you can still see the metrics, and the metrics will still be there. So it distributes the overload evenly. Then the routers are concurrent, so it's a big upside in terms of performance. Very important things is that each host has its own processing queue and its own sender, so the hosts are completely independent. This is probably the main problem that we had, is to have the targets totally independent. So when there are failures, there are outages, there are things that go really, really wrong, then nothing will interfere across hosts. So if one host goes really bad, that will not in any way be reflected on other ones. So they're completely isolated. And so if you just look in general, this model has a unidirectional flow. This makes it much more reliable, much easier to reason about in general. And it's just harder to make bugs, honestly. In my experience, when I design systems, having a unidirectional flow and simple execution flow is extremely beneficial, and it also makes the thing more resilient. Just from the point there's less bugs in it. That's it. Yeah. So the design is another reason for resiliency, for performance. I could call this design simple, but that may not be entirely evident. But if we compare this design to the design that we worked with before, that some other systems have, it's fairly simple. So moving on, another thing that makes Nanotube so nice, and that's why we did it, is we have native support for Kubernetes. And how we do it is we have inside the Kubernetes, here on the left, the big box is one Kubernetes node. And in that node, we have the pods running that run the actual services. And the Nanotube, in this case, it can run in a Kubernetes mode. In that case, we call it Nanocube. And it runs as a daemon set. So to remind, the daemon set is something that when we run it in a Kubernetes cluster, it will run exactly one copy of it on each node. So on each node, we can be sure that we have one copy of Nanocube running, and that Kubernetes makes sure that it always runs there. If it dies, it restarted. And this is this thing in red. And how it works, it talks to the container runtime API, and it detects the pods that would like their metrics sent to Graphite. But we only do this for the pods that are labeled in a specific way. So there is a predefined label, say Graphite metrics enable, that we look for. And when we we ask the container runtime API if it can suggest some pods with that. And when it says, yeah, okay, here's one, we get the information about this, the container of this pod. And in this case, I'm talking about infrastructural container. This is a container that is made before the real service containers, and it creates the networking namespace, for example. And then what we do is we magically, with the stars sparkling, open the TCP port inside the spot networking namespace. And what this does is for the containers, the service containers that runs inside this pod, it looks as if they magically have a local port open that they can send the metrics to. And so for the users that run the service and that run the containers, it's very convenient because it looks exactly the same as it looks on a normal server box. So it's extremely convenient when, for example, migrating from bare metal boxes to Kubernetes, because you don't have to change anything. Also, you don't have to worry about how the service discovery should be done, any of this. Just send metrics to a local port. That's it. That's it. Don't have to worry about anything else. So the containers send the metrics to this TCP port, which actually is the open port of Nanotube. And then the Nanotube sends the metrics out to the main nanotubes, which are the main routers, and these later send the metrics to the storages. And then the question is, like, why would you do this like this? First of all, this is a native Kubernetes abstraction in this particular case. This allows to keep the Kubernetes and promises of Kubernetes intact. And we also have the isolation between the services. There is much less problems with noisy neighbors. We have strong guarantees from Kubernetes as well. We also, when running like this, get the metadata. So we know when connecting to the service and when getting data from it, we know which services are sending the data, and we can monitor how much. And this is very important. Because it's a big problem of Graphite to handle large numbers of metrics. And it's very common in Kubernetes to have very large numbers of metrics, very high metrics churn. We usually call this high cardinality metrics. Because it's very easy just to fire up hundreds of pods, make metrics, and then fire up again, make new metrics. So we are not talking about just the number of data points that come per second. That is not a big problem. Can be, but it's not the main one. But the problem is that way too many metrics are created, and because of that, there will be a problem on the storages, because Graphite it's not always easy, and it's not cheap at all to store too many metrics. And with metadata, we can have visibility, and we can have control over how metrics are created, how metrics can come in. And this is also the reason why we only pick up the labeled pods. This is also to have the control over the influx of the metrics, how many metrics go in, and to have control over the adoption of the service, and to prevent the explosions of the number of the metrics and keep everything nice and stable, fully monitored. So with this, we can have a native Kubernetes support that holds up all Kubernetes abstractions, gives all the bonuses I just mentioned, as compared to the things that we used before. So talking about the future, so the next steps and ideas and challenges that we got. So in my opinion, we can have even better performance than we currently have. So better performance means saving boxes, saving costs. So it's always great. And also, we are looking to have the routing based on metadata, in particular source-based routing. I have mentioned like some slides before that we have several clusters of nanotubes for routing depending on the source. And we would like to avoid that, because if we merge the clusters, then the load is more evenly distributed. And this means better resource utilization and cost saving. Also, when there is no clusters, we can have better management of peak loads. There will be more boxes that the load will be spread across. Also, it's easier to maintain. And just metadata routing by itself is great because it can be used for different things later. For example, we can route differently based on a tag that is responsible for the owner of the metric or the type of the metric. And just the metadata support in general is very valuable for metrics types and things like that. Another thing is governance and multi-tenancy. A lot of work with this is done on storages, but this presentation focuses on Nanotube. So we would like to have the usage stats. We would like to have the ownership tracking. And again, a way to do that, in my opinion, is through metadata. This is the things that we work on. And we also would like to have better blast control. This is what I managed in the previous slide when talking about having various ways to limit metrics coming in, like fault labeling. This is especially important for Kubernetes because there can be very high numbers of metrics coming in. And so this is another thing that we look to implement and we're looking for. In general, there are a lot of interesting challenges and a lot of interesting problems still to work on that we are currently working on. And hopefully in the future, I'll be able to talk about them a little bit as well. Yeah, so I just want to say thanks. And here is the URL of the repository and also the QR code with the same URL. And we are welcoming contributions to our projects. We'll be very happy to help you with your first issues and help you adopt the Nanotube in your own organization. And also, if you just have any questions, come along and ask them the issues on GitHub. Yeah, thank you.
Thank you very much, Roman, for this presentation. Really, it's really a huge challenge what you've described, and the solutions that you've come up with are really, really interesting. And good luck also with the further challenges that you pointed that you still need to solve.